As previously mentioned, exponential and logarithmic models are extremely useful in various population and radioactive decay modeling situations. This is the simplest growth and decay model. It says that the amount of material or population size present at time t is exponential with some constant in the middle and some initial amount p naught. So let's just label this equation to keep track of it. On the left-hand side, we have the amount or number of things at time t, whereas on the right-hand side, this k stands for the growth or decay constant, depending on the scenario that you are describing. If it is a growth constant, it will be positive. If it's a decay constant, it will be negative. T is, of course, time, and then this P naught is the initial amount. So let's actually sketch the two different scenarios, the positive or the growth scenario and the negative or the decay scenario. So in terms of the graphs, both are exponential functions, and if we're thinking that whether the growth or decay occurs with time, we will be only looking at the positive values of t. So if the constant is positive, that represents exponential growth, I'm going to have some kind of initial amount of, let's say, population or the number of infected individuals. And then afterwards, my function will grow, whereas this is P naught. If K is negative, that represents the decay scenario. I will start with P naught, but my function will exponentially decay. So here I'm not showing you the tail on this end, it's right there. On the decay constant, the negative will be coming from the side of the increase, and then it will be decreasing afterwards. Also notice that this initial amount, we just take the convenience of labeling it P naught, but if I were to actually plug in time equals 0 into the entire equation, I would get P naught e to power k times 0, because now t is 0. And then, of course, this is e to power 0, which is just 1, which results in P naught. That is why that constant in front of the exponential portion here is the initial amount. Australian cane toads, or giant toads, were introduced in Australia in 1935 with the purpose to fight cane beetle, which at the time was the main pest of the sugarcane, which was a big industry in Australia. The native land of these guys is South America. However, their introduction, while seemingly theoretically reasonable, really backfired. What happened was there was a certain asynchrony in the reproductive cycles or life cycles in general of the cane toads and the cane beetles, which meant that while the cane beetles were eating all the sugarcane, the toads were more or less hibernating. The other issue was the fact that the toads reproduce greatly and they have really, really voracious appetite, which is why they were supposed to be really good for eating cane beetles. Unfortunately, the other huge issue is the fact that their skin is extremely poisonous, which makes them almost invincible to all types of predators. And in fact, they've been labeled one of the worst pests because they have no natural predator and they're also poisonous to domesticated animals as well. Since then, the government has tried a number of techniques to control the population and more or less not really successfully, which serves as another lesson that if you mess with an ecosystem, you might have another thing coming. Now, because this is such a big issue, their population and particularly the spread of the territory they're covering have been greatly studied. They've been studied since 1939. They were introduced in 1935. And we will first use this simplified model to track or try to model what their territorial coverage has been throughout the years. Year 0 will correspond to the first year we have data for, which is 1939. So the first question is, if I have two pieces of information. In 1939, they occupied 35,800 square kilometers, and in 1949, they occupied 73,600 kilometers. I would like to find what we call a solution to this model, which really means finding the unknowns, which in this case are the initial population and the growth/decay constant. Okay, so let's write out all the pieces of information that we actually have here, which of course is, first of all, in the year 1939, we have that the total occupied area was 32,800, which means that at time t equals 0, once again, I can either remember that this stands for the initial amount, or I can plug in t equals 0, and we will see that A naught is equal to 32,800. The next piece of information that I have something about is the year 1949, which then of course corresponds to t equals 10. And then I know that the total occupied area was 73,600. So this number corresponds to the right-hand side of this equation. I already know the number for A naught, R is what I'm after, and T will be 10. Okay, so overall, I have the equation that 73,600 equals to A naught, which is 32,800 e to power R, which I still don't know, times T, which is 10. This is really good news because this is an equation with only one unknown, R, and I can solve it for R. So solving for R here, I will have that it is the logarithm of 73,600 divided by 32,800 all over 10, and that comes out to be approximately 0.081. Okay, which means that now I know all of the constants in my model, and I can rewrite this as A naught is 32,800 e to power R, which is 0.081 t. I can see that this is indeed a growth model because the value for R is positive. And with that in mind, I can approach the second part of the question that says, now using my newly discovered model, I am going to estimate the area occupied by toads in 2020 with the, of course, assumption that the model back from the 30s and 40s still works. So with no great changes to the environment. So what happens in 2020 is the total amount is going to be 32,800 e to power 0.081 times t that corresponds to 2020. Well, t equals 0 corresponding to 1939. So t that corresponds to 2020 will be 2020 minus 1939. Okay, so plugging all of this back in, I'm going to get approximately 22,856,304 kilometers square. So of course, unbounded growth ends up in really, really fast spread if nothing actually happens in terms of the control of the pest. The other really interesting application of the exponential functions is Newton's law of cooling, which states what the temperature of an object is in terms of the ambient temperature of the environment, the initial temperature of the object, as well as some cooling constant K. Now, the first thing to notice here is that this cooling constant K, because the object is cooling, is going to be negative. You can think of the situation as, let's say, a cake taken out of the oven into a much cooler room, and the cake actually being cooled down in the ambient temperature of the room. Let's consider, first of all, the general setup. So let's think about what actually does happen at time equals 0. So if I plug in t equals 0 into here, what am I going to get? I'm going to get Ta plus T naught minus Ta e to power k times 0. Now, of course, anything to power 0 is just 1, so this is 1. So overall, I have Ta plus T naught minus Ta. Then the two Ta's will cancel, and I'm going to get T naught, which means that the notation is reasonable. The temperature at time 0 is in fact T naught. Another thing to think about is, what do we expect the eventual temperature of the cooling down object to be. So let's take a limit as t goes to infinity of the temperature function. So I have the limit as t goes to infinity of Ta plus T naught minus Ta times e to the kt. Now, it is essential here to remember that my constant k is in fact negative. So this guy right here is negative. And remember what the e to the negative power looks like as a graph. It is going towards 0 on the right-hand side, which means that this portion approaches 0. Anything times 0 is 0, which means that this part of my function approaches 0, and therefore, as the limit, I just have Ta, which means that eventually the cooling down object will reach the temperature of the ambient environment. That also makes sense. If I take a cake out of the oven and place it at room temperature, eventually the cake will in fact reach the room temperature. And that justifies what we might think of as a rough sketch of the graph of this function. So let's say this is my ambient temperature right here. That's something that my object is going to approach. It's not going to do below it unless we introduce something else into the picture. And the initial temperature, T0, starts up above it. Again, we're thinking in terms of cooling down, not heating up. So the temperature of my cooling down object will approach the ambient temperature, never going below it, but probably eventually actually reaching it. Okay, so let's see how this can be used in applications. One of the coolest applications that one can think of in terms of cooling down objects is how a blacksmith actually tempers the metal and then cools it down before they can temper it some more. So let's take a look at how a farrier works on a horseshoe. In order for that, let's first of all take a look at what does that actually mean? What does the farrier's job actually involve?
The goal of the unit is always the horse, and the horse is the most important priority that we have.
I'm just going to take the shoe off my crease nail pullers.
And without the horses, we wouldn't be a mounted unit. So everything that we do here is for the benefit of the horse.
My little friend, how are you? I often try to talk to these animals because, like anything else, when you're having anything done, it's always easier to get done when you're talking to something or someone.
The mounted unit was established in 1858. We're the oldest and largest mounted unit in North America. There's a very special relationship between a mounted police officer and the public. We have 4 facilities spread throughout the city. We have over 100 officers, over 50 horses, and 3 full-time department horseshoers on staff. They're here every day.
That's really the goal of the farrier. We try to keep the horse in service and comfortable and safe. Because believe it or not, it is 2,000 pounds of dead weight on top of 4 tiny feet. But I've been shoeing this horse for almost 10 years straight, and he knows me, I know him. And that's really the goal of the farrier. We try to keep the horse in service and comfortable and safe. It is a dream job. It's not even a job, really. We're kind of spoiled. What's up, Hanson? You're all right, man? I know.
So as you saw in the video, the farrier actually molds the horseshoe to the horse, which means that he or she has to constantly work on the shoe until it reaches the right shape. So once they are working on it, they have to, before putting it on, cool it down to a temperature where the horse will be comfortable at. And this is what this question is about. The question says that while the horseshoer is working on the horseshoe, the actual metal is heated up to 400 degrees Celsius to be, in fact, Mendy enough. And then they dunk it in 25-degree or room temperature water. The water around the horseshoe stops boiling in about 30 seconds, and the horseshoe is safe to put on the horse when it's at approximately 60 degrees Celsius. What we're wondering is, when does that happen? So how long should a farrier keep the horseshoe in the water for it to cool down to the temperature that the horse will find comfortable to be put on? Okay, so this is our Newton's law of cooling. This is just a general formula from the previous slide, and let's fill all the information in that we have in this question. So the left-hand side here will be the temperature of the horseshoe, TA, the ambient temperature. Of course, the horseshoe gets dunked into the water, so the ambient temperature corresponds to the water temperature, which in this case is 25 degrees Celsius in both cases here. And then T naught is the initial temperature of the horseshoe. While the farrier is working, it's 400 degrees Celsius, so this is 400 degrees. The one unknown is still the cooling constant, and that is something that we're going to have to solve for using other information provided in the question. Now, before we do that, let's put together what we have so far. So I have 25 plus, and then this is going to be 400 minus 25, which is 375 e to power k t. So this is my best model so far. Still don't know k, but I have all of the other constants in place. So the other piece of information we have not used yet is the fact that the water around the horseshoe stops boiling in 30 seconds. I know that the boiling point of the water is 100 degrees Celsius, so it's safe to assume that in 30 seconds, the temperature of the water around the shoe is 99 degrees Celsius. So let's record that. In 30 seconds, the temperature, in 30 seconds is 99 degrees Celsius. Now, instead of writing it this way, we're going to write it inside our model. So the temperature is 99 degrees at the time of 30 seconds. Okay, so just matching the model to what I have, replacing the time with 30 and replacing the left-hand side with my actual temperature, I have an equation like this. The only constant here is K, and we can easily solve for that. I'm going to skip the steps, but you should get the number that is approximately minus 0.0541. This is a really good time to stop and make sure that you're on track in terms of constant. The cooling constant has to be negative in this case, which it is, so it seems like at least our algebra is working out okay. Now the question is, when can the farrier put on the horseshoe? And that is when the temperature is at 60 degrees Celsius. So what we want to know is, for what time t is the temperature equal to 60 degrees Celsius? And once again, we're going to take it through the model here. So the temperature on the left-hand side here has to be 60 degrees for the horse to be comfortable, and the right-hand side is here. Now I know my constant K, and I will be after the value for the time t on the right-hand side. Okay, so altogether, the equation I have is 60 is equal to 25 plus 375 e to power k, which we've just discovered was 0.0541 times t. Once again, this equation simply has one unknown, which is t, and we can solve for it. I'm also going to skip the steps here, and t will work out to be approximately 43.8. This is time. Be careful in units, it says seconds here, so our time all along was in seconds. So the horseshoe will be cool enough, cool down to 60 degrees Celsius, and therefore be able to put on the horse in 43.8 seconds. Please make sure you actually go through these simplifications and solve for these values, just to make sure you have enough practice solving exponential and logarithmic equations here. One word of caution is, it's easiest to solve these equations if you first isolate the term that has the constant in it. So do not apply logarithms to both sides until you have the e to whatever power completely isolated. So move, let's say, 25 over to the left here, then divide everything by 375, and then apply logarithms. Make sure you go through this, because there will be more problems like these in class and of course on tests.